Hi everyone, this is a MOOC course on register transfer level design of digital system, and this is me Muhazam giving you the lectures for this MOOC course. Since this is a MOOC course which should be available online, we will make and to be enrolled by any student that has internet connection in the world. We will design this course to be as flexible as possible for anyone that meet our requirement. This RTL design course is an advanced topic in digital electronics design, and the students are assumed to have the basic understanding of the fundamentals and intermediate courses in digital electronics. The fundamentals are the knowledge on gates, K-map, truth table, Boolean algebra, flip-flops, and the finite state machine, FSM. And for the intermediate part, we assume you already know about how to code with Verilog, and the more complex module of digital system, either as drawing or as Verilog code. For example, the functional modules of adder, multiplexer, etc. And also the concept of datapath and multifunction register. This course is suitable for final year students that are doing RTL design in their projects. Also suitable for courses in a university that is offering an elective or specialized course in digital electronics as the introduction course for example, as introduction course for example, ASIC design, programmable processor design, ARM design, etc. Or it can be the first course for master level digital electronics or computer science courses that has some emphasis on hardware. For this first lesson, you will be able to have the recapitulation of these two basic idea, the basic digital electronics building blocks and the Verilog code for them. First, let us go through briefly about multiplexer. Multiplexer is a functional module or a building block in digital system that choose one input from so many inputs that come to it and pass it to the output. The input and output can be multi-bits, which means when we select one of the input can be 2, 3, or any number of bits. but the number of input, but the number of bits in inputs and output must match or must be the same. This is how we draw it. The shape for multiplexer is normally a trapezium. We will have a few lines of selector. Let's say in this case, we are drawing for a multiplexer with 3-bit selector, which means the number of inputs that can be in the multiplexer is 8, and then we label them from 0 to 7, and there is only one output. So the individual lines here may not be single line. It can be more than 1 bit, but they must match from input to output. Then how do we write multiplexer module in Verilog? If let's say we want to have the multiplexer in pure combinational wiring, this is how the code basically look like. We just put an assign statement to the output, taking the input individually, and we end it with the possible combination of the selector, and then we OR each of the combination separately. There is a special case where the multiplexer is only taking 2 inputs going to 1 output. The selector is obviously 1 bit or 1 line selector. If that is so, this is how we draw it, and the code for it is assignment to the output using conditional operator. If the selector is true or 1, we take the input 1. Otherwise, if it is false, we take 0. So this is how the drawing of the multiplexer shows it. But if the multiplexer somehow need to be inside an always block, then the multiplexer need to have register or latch. So in that case, we can use case block to assign the value to the output of the multiplexer. So let's say in this case we have a 2-bit selector, which means it is 4 to 1 multiplexer. We list all the possible combination of the selector in the case block, and then we assign the value of the individual input to the output in each of the cases. Next building block is the arithmetic operations. Obviously, there are adder, subtractor, multiplier, and divider. The drawing is easy and very straightforward. If it is adder, then there will be 2 operand coming in, and then the addition comes out. The same to subtractor, multiplier, and divider. The code is also very straightforward. Arithmetic operation, if it doesn't involve any register, we just use the assign statement. A assigned with B plus C, B subtract B minus C, B star C, B slash C. These are This corresponds to the addition, subtraction, multiplication, and division operation respectively. Next is multifunction register. Multifunction register is the register that we want to equip with a few operations, and the operations on it is determined by a selector input. Internally, it has multiplexer, but normally we do not draw it in our data path drawing. And this is how it looks like. This is a register. This notch is to show that it is a register with a clock input, a few selector of a few bits coming on one side, and the top and bottom are the input and output. Obviously, multifunction register will need different Verilog code for each of them, so it is rather difficult to generalize it, but this is one example. Let's say we have a register, 8-bit register with 4 functions. If the selector is 0, it is a reset function, for example. So we have a case block like this with, if the selector is 0, we assign the register with all 8-bit of 0. If it is 0, 1, we want the operation of parallel load from the outside. So we assign register with non-blocking assignment from data in. And let's say if the selector is 1, 0, we want to toggle the bits in register. This is how we write the equation. And let's say if the selector is 1, 1, we want a complete set of the bits in the register. These are the 3 most important building blocks that we normally cannot avoid in any design. But there are a few minor but very specific but have very specific requirement and functions in certain digital system. We will introduce those specific building blocks in the respective design that we will show you in the chapters to come.